Swayam Prabha. Digital India. Educated India.
Very good morning to all of you. So I think this is a course in which you're talking a lot about precast concrete. So a lot of what I'm going to say is actually applicable more to what we do on site, although some of it you can probably relate to as far as concrete production and precast scenarios is also concerned. We are going to talk in this session on performance-based specifications for concrete durability. Now, this is a topic which has gained a lot of traction in the last few years because there's an increasing realization that protecting our structures and making them last longer has to be a very clear motivation for us going forward with the kind of different kinds of expectations that we now have from our concrete that is used in structures. So I'll primarily talk about what is the issue currently which we are not resolving properly as far as concrete design is concerned. What are some techniques which we can adopt to ensure that we can have a good durability that can be brought into our concrete structures. Okay, so what I'll cover today is first is how to design for durability, and then talk about what a performance specification actually is, and then we'll also discuss some of the ways in which we can implement performance specs and what are the challenges involved in this, and some ideas about how do we move forward as far as concrete control, production control is concerned. Now, you all know very well that concrete is subjected to a host of durability problems during its life cycle, depending upon the kind of exposure environment that you have the concrete working in. You have external sulfate attack, which is brought about when you have concrete in sulfate-rich environments, but perhaps in some conditions, the soil has a lot of sulfate. In some conditions, the water that is brought by the groundwater, or maybe you have some brackish water which can have sulfates and chlorides in it. You can have acid attack, which is a very specific circumstance when you have acidic conditions prevailing in the water that comes into direct contact with the concrete. This primarily is seen in sewer pipes, where you have the issue of the crown corrosion. That's what you're seeing here. In the sewer pipe, the entire crown, the paste or the cement paste has been completely washed out, and you only have the reinforcement left. And eventually, in acidic conditions, the reinforcement also will give way, right? Reinforcement corrosion is perhaps the biggest problem that you have in concrete in service. This is primarily caused either because of the presence of chlorides, which causes problems like pitting, or you can also have issues of carbonation, which basically happens whenever you have less cover in your concrete structures. And in marine conditions especially, you have a combination of chemical and physical attack problems that leads to a lot of damage, which is not easy to control unless you have a proper strategy for design of the concrete beforehand. Okay, so all these durability problems are very clearly associated with the presence of water, right? Water is either needed for the reactions to happen, or water is needed for the reaction to propagate. Without water, none of these durability problems will actually affect concrete. In other words, you need some moisture to carry forward these problems, right? If you keep your concrete dry and free from moisture, many of these problems will cease to exist. You'll really not have any issues as far as the long-term performance is concerned, but we know that's not going to happen. During lifetime, concrete will get re-wetted multiple number of times. It will dry out and get re-wetted, and presence of water is absolutely impossible to avoid, unless, of course, you are talking about interior concrete elements, in which case that direct exposure to water is not really there. But even there, we managed to create all the kinds of exposure possible because we have a lot of cracking in the concrete, and especially from toilets, water can get in contact with any of the structural members. And when wet conditions persist, you obviously have an issue of either chemical attack or corrosion in reinforced concrete structures. So it's very important for us to devise ways in which we can keep water out of the concrete. And how do we do that? We make concrete impermeable. The first line of defense as far as concrete durability is concerned is to make it impermeable, to ensure that water finds it extremely difficult to get through the concrete, right? This is not going to be of any use if we have cracks. However good we make concrete quality, if we don't have a means of avoiding cracking, there is no way that we are going to achieve this condition. So all I'm going to say is valid only if the concrete is uncracked. Okay, if the concrete is cracked, then we have limitations of the crack width, as you all know. In structural design, we limit crack width based on the exposure condition. But then, how often do you actually measure these crack widths? In practice, nobody is really doing it. Okay, and only in some specifications, it's a mandate to actually do the measurement of crack width also. But in many cases, we just don't seem to pay any attention to it. So please remember, avoiding cracking is perhaps the most important aspect. I'll touch upon that once again when I talk about durability planning. Okay, so how do we take care of durability conventionally? What do we do? Any pointers from the audience? What do we do to take care of durability conventionally? Providing cover. We provide sufficient cover, right? What else do we do? We use higher grades of concrete. How do we achieve that? By lowering water to cement ratio, right? We achieve higher grades by lowering water to cement ratio. And when we go with the lowering of water to cement ratio, not only do we make our concrete less porous, we also make it less permeable. So that is a direct influence on making the concrete more durable, right? What else do we do for durability? You can do coating either of the rebar or of the concrete, depending upon the kind of condition you're trying to protect the concrete against, right? So these are some of the conventional options, but there is no real implicit example of using durability in the design of the concrete itself, right? All of these things you said, yeah, these are prescriptions that you can follow to get durable concrete, right? Lowering water cement ratio is a prescription that you actually follow. But how often do you actually measure the actual water cement ratio of the concrete that is delivered on site? What if somebody has added extra water just to improve the slump when the concrete is delivered on site? Are you checking anything? No, you only have the water to cement ratio that you have on paper. So you are only prescribing, you are not really demanding the performance. You're talking about cover. We say that for concrete in an extreme environment, for a column, the cover should be 75 millimeters. We use cover blocks. We do the concreting procedure, which may actually, vibration may dislodge the cover blocks. In some conditions, your cover may reduce to more than, reduce by more than 10 to 20 millimeters, putting completely off your calculations for durability design life of your concrete structure. So how do you safeguard against that? You're not really demanding that performance. You're only prescribing, right? So that's where we need to go forward. I'll come back to that. So first and foremost, all structural engineers, I know many of you are structural engineers, have this clear understanding that durability is a function of compressive strength. So to increase durability, you increase the compressive strength or the grade of the concrete. This is both correct and wrong. What I mean to say is there are means of increasing durability without changing your strength also. One example I'll give you: in the Chennai Metro Rail project, they were designing these tunnel segments, which were supposed to be structurally only of 45 megapascal grade. Okay, but the durability condition was so rigid, and the specs did not allow for the use of supplementary cementing materials, because of which the concrete actually was designed for a much higher strength. When we actually took cores from these segments and tested, the strength of the concrete came to 90 megapascals, just to meet the durability criteria, right? So that means we are not designing for durability. We are only saying, okay, if you want more durability, get more strength. But that, you know very well, for a 45 MPa concrete, if you're designing 90 MPa, it's absolutely useless design, right? You're wasting resources. Why would you want 90 when your actual design requirement is only 45? So that's what I'm trying to say. Durability is taken simply as a function of compressive strength. We prescribe the cement type. We prescribe the binder content. That means how much cementitious materials are available, and the water to cement ratio for what we assume will be durable concrete. We specify the cover for the service environment. All these things are already what you have already said. We seldom actually check the cover on site after the construction has been done, right? We do an inspection that the cover blocks are placed properly. That's about it. But even there, a lot of issues are lacking. People don't really inspect well enough to see whether the cover blocks are in place, whether they've been tied properly, whether they are in danger of actually moving, reducing the cover and so on and so forth. So all of those things are not carefully assessed on site. In rare cases, in some specifications, durability tests are actually specified, but these are done on specimens that are stored in ideal conditions, right? The cubes that are made in the QC lab are the ones subjected to your strength testing and also subjected to durability testing. But nobody actually checks the actual durability of the concrete and the structure. First of all, it's not easy to do, and not many people have the wherewithal to understand how to do it. Secondly, doing tests on the structure can sometimes be prohibited by the client. They can say that, okay, we don't want you to test something on our structure. Don't go around hammering our structure, right? Like one of the tests that people do for checking the quality of plaster that you put on the walls is taking a hammer and trying to break the plaster. I don't know why you would test something by breaking it, but still, they feel that if you can't drive a nail properly through the plaster, it's not done properly. And we had this issue in one of our hostel blocks also. People were able to actually scratch off the plaster directly by their fingers. They didn't need any nails or hammers or anything like that. But yeah, that indicates poor quality of the plaster, definitely, right? But here, in many cases, you will not be allowed to test directly on the actual structure. So that's why it's insisted that you test your concrete quality on specimens that have been cast and stored in ideal conditions. But very often that doesn't give you the true picture. Now, what questions we need to ask as engineers is, are we really achieving the goal of durable concrete by doing all of this, or simply ticking boxes? Yes, I've chosen the right cover. This code says that I need to use so much cover. I've used this cover by using the cover block. I've used this cement. I've used this kind of an aggregate, whatever it is. I've just ticked several boxes. We have not really thought about whether what we are doing in practice is actually going to get us durability in the site or not. And that is something that we want to change going forward, treating concrete like any other material and ensuring that we are able to apply scientifically proven concepts to the study of concrete durability. And that's what we want to do in performance specifications. So if you think about durability, you have two major aspects that are controlling durability. One is the concrete system, where you have the materials, that's the binder type. Let's say you use ordinary Portland cement, Portland porcelain cement, Portland slag cement, and many other different types of cement that are available. The binder content, how much cementitious material do you use, right? In IS 456, you would have seen that for different categories of exposure, mild, moderate, severe, very severe, and extreme, the code says that your concrete should have minimum so much grade of concrete, minimum so much cement content, and maximum so much water cement ratio. That's a prescription given for durability in that particular environment, right? So that's your prescription for the material and the material content, binder content. The type of aggregate that can be used, of course, mostly the type of aggregate is driven by what is available locally. In Chennai, if I demand that I have to use quartzite aggregate, that is stupid of me, right? I have to use what is locally available, which is granitic, right? If I go to Delhi, I have the option of using quartzite. If I go to places where you have aggregates that are of a reactive nature, like New Zealand, for example, which has volcanic rock, and all the aggregates are basically reactive in the cementitious medium, leading to long-term problems. Then you need to think about, okay, how do I design against that reactivity to make sure that that reaction is not detrimental to my concrete? So all of those are part of your material selection process, and type of admixtures that you use, and finally the mixed design of the concrete. Then you have the entire process, right? Concrete is mixed in a central mixing plant or on site, depending upon the kind of options that you have. You then have the transportation of the concrete to the site at which the concrete needs to be delivered. At the site, concrete is getting compacted either by external vibrators or by formwork vibrators and so on. And then you have curing. You also need to worry about the temperature of the concrete. In some instances, for instance, if you're talking about mass concrete, you need to worry about what the initial placement temperature of the concrete is. And finally, the workmanship, right? How is the quality of the labor that is working with the concrete on site? Are they doing a good job? The problem is none of these are being captured in your code, right? If you look at the disclaimer that the code gives, is saying that you will produce a durable concrete if you pay attention to all these prescriptions, assuming that all other processes of concreting are done properly. Now, we know very well in 90% of the cases, this is where the problem lies, right? We know very well. Can we not look at specifying a process which can bring in these aspects also? Again, that's where we are going with the performance specs. Now, of course, the other side of durability is the type of environment for which you're designing the concrete, the aggressiveness of the environment. We have to obviously work with it. We have to ensure that the aggressiveness that's understood based upon the kind of deterioration that is likely to happen. For instance, if I'm going to be designing a concrete structure in Chennai, what kind of aggressiveness should I consider? Chlorides, definitely. Humidity, right? Because humidity affects various other processes. It's not a direct deteriorating factor, but yes, it affects other processes, right? The temperature, high temperature in some instances, and that could lead to some volumetric changes also that leads to further cracking. That's mostly at the early stages. Yes, all of these things are affecting the quality of concrete as it performs in a given environment. If I'm in an inland environment, I don't worry about chlorides, but I may have to worry about carbonation, right? I may have to worry about sulfates if the soil is rich in sulfates. So those are the kinds of aggressiveness that you need to consider in the design. And it can be of the physical type, like for instance, if you're designing a spillway structure, you know that in a dam spillway, there'll be a lot of abrasion and erosion that is caused by the boulders that are moved by the water. At the bottom of the spillway or at the bottom of the dam structure, you'll have cavitation. If you have a concrete structure that is in a very cold environment, you have possibilities of freezing and thawing. All of these are volumetric changes that can affect the quality of the concrete. But chemically, your concrete may be in contact with sulfates, with chlorides, with acidic waters, and so on, which will cause different types of chemical issues. Dissolution of the concrete, leaching of the cementitious materials from inside to the outside, expansion of the concrete because of some reactions that may happen, like sulfates will produce expansion, and alteration of the cementitious compound that leads to fall in performance of the concrete, right? So all of the different types of exposure conditions need to be considered when you design the concrete. So all of that is definitely part of the process, but your specification needs to pay attention to what is happening. Now, if you look at many of the specifications for infrastructure projects taken up in the country, they uniformly give prescriptions of two durability tests. One is a rapid chloride penetration test. The second is the water penetration test under pressure. Okay, RCPT and WPT. These are the two tests which are prescribed almost in every infrastructure project, depending on, doesn't matter where you are. Now, I don't know whether that is a good way to move forward. Of course, it's a way to control the quality of your concrete that you're putting into the structure, no doubt. But in terms of prescribing tests, they are not really paying any attention to the kind of environment that your concrete is actually servicing it. Right? For instance, if you're thinking about an acidic exposure condition like concrete in a sewer pipe, why am I worried about water penetration under pressure? I need to start paying attention to how the concrete resists acids, right? Why am I worried about rapid chloride penetration? Except for the fact that it also is an indirect measure of the permeability of the concrete. That's about it, right? I'm not really paying much more attention. So both these tests are actually addressing permeability and not really the durability in a specific environment. They are indirect measures. But what the problem is that we are left with very few test methods that are rapid and can be done fast enough for us to include them in the concrete mix design process. If you have to actually set up exposure tests for the specific environment, it will take us forever to design the concrete. If I have to do a sulfate exposure test on concrete, the result may take me nearly 1.5 to 2 years. By the time the project will be over, right? Of course, in India and most of the construction projects, if the concrete is to be placed tomorrow, they want the mix design today, right? They ask you for the mix design today. Sometimes even the concrete was placed yesterday, they want you to work the mix design today. That means we just are not given sufficient time for designing the mix. Then how do we even take care of durability at all? All we are doing is the strength-based design, right? So again, that means that we need to pay attention to durability a lot more during the material selection and design process itself. Now, these aspects of material and process need to be somehow captured in the specification if we really need to make a difference as far as durability is concerned. Otherwise, we are just prescribing, right? Like a doctor prescribes medicines for you, but if you don't take care of your health apart from taking the medicines, eating your food regularly, having a good sleep schedule, exercise properly, those medicines may not have the right effect, right? So the process is as important as the choice of the materials and the prescription itself. And if you're not paying attention to the process, you're often going to cause more problems on site. So the specification has to be robust enough to capture the process, and that's where we are looking at performance-based design of concrete structures. So general approaches to durability design, as we already discussed, the prescriptive approach, what we are following currently in codes is the deemed to satisfy approach. If you use this, this and this, your concrete is deemed to be durable. There's another approach, of course, which is an expensive approach, is that we use inert materials which will not react. For example, instead of reinforcing steel, we use stainless steel. Right? We know that stainless steel is going to be stable for much longer time. It takes a lot for stainless steel to corrode, either with chlorides or carbonation. But then you know very well that stainless steel is an option that is extremely expensive, right? Or sometimes we use coatings, right? Coatings for the concrete or the steel can also be used in most codes and most design strategies. These are called additional protective measures, APMs, right? APMs can be used in addition to designing concrete for durability, but they are not the only guard against deterioration in the long term. Now, the other approach is the performance approach, where you have the performance-based tests and indicators. For instance, this RCPT, WPT, and all that, those are indicators of concrete durability, and they help us in selecting the material based on a concrete quality ranking that we can do at the time of mixed design. I choose different ingredients for the concrete, I design it and test these durability values like water penetration, chloride penetration, and so on, and then select my material according to that, right? The other aspect is, of course, if I have sufficient amount of data in lab studies, I can create models with it and verify using field data. In the long term, that is perhaps the better way to go forward with performance specs, because we can't keep doing testing day in and day out, because to select the material correctly, if you have a workable model, that's the best strategy to move forward. Okay, so these are some of the approaches. As I said, currently we are following the deemed to satisfy approach in our codes, where we prescribe things, we don't measure things as well. So performance approach is where measurement is an integral part of the durability design. So just to give you some examples, if you look at prescriptive specifications, you have your curing duration and method. Let's say somebody says you use ponding for 7 days or wet Hessian curing for 14 days. That's basically a prescription. Okay, performance is whether people actually do it on site or not. Very often you may have seen structures where the Hessian is on the concrete, but it's not wet. What is the point of curing like that, right? So that means what is on paper did not get translated to the site. Minimum cement content is a prescription. Okay, your binder type, whether you use OPC, PPC, PSC, or different types of cement that you have, that is a prescription. Maximum water cement ratio is also a prescription. So a prescriptive spec gives methods, materials, processes, and procedures that instruct exactly how to carry out the work. So that means the person who's doing the construction, the contractor as well as the concrete producer, they don't really have many options to play with. They are straitjacketed that they have to actually use only this, and this material to get your structure done properly. But in a performance specification, it does not place any requirement on the combination of materials that you use as long as you meet the performance, right? The emphasis is on requirements of the finished product, like compressive or tensile strength, cover depth, maximum shrinkage, and permeability. So these are all performance parameters which need to be addressed by a careful assessment on either laboratory specimens or structure itself. Okay. Now the issue is cover depth. Cover depth is also a prescription, right? Sometimes we say, okay, you need to have so much cover in this kind of an environment. But where does it become a performance spec is where we start measuring it. How do you measure the cover depth? Yeah, you have electromagnetic scanners basically which measure the cover depth, and of course, it's going to be cumbersome to actually apply this to all structural elements in your construction project. But you can choose a percentage of your elements like 2% or 5% and apply a cover meter test to determine whether your concrete cover is adequate or not after construction, right? Post construction cover checks. That becomes a performance parameter. Just specifying it does not make it performance, but that becomes a performance parameter. Now, right off the bat, we know that compression or compressive strength or tensile strength, depending upon the kind of job that you're doing, tensile strength or flexural strength primarily comes into play when we are talking about pavements, right? Concrete for pavements. But for buildings, primarily we measure compressive strength. We measure it at wattage, 28 days, right? Sometimes at 7 days also. In addition, we always measure at 28 days, right? Now, what happens if the strength requirement is not met? At 28 days, I've tested my cubes and I'm not meeting the requirement. What do I do? Sorry? We can do NDT to establish what is the condition of the concrete in the structure, because we have tested here on specimens. Of course, we need to analyze, okay, what went into that concrete, the batch of the cement, look at the test reports carefully and see whether everything was done properly or not, right? In the structure, we can do non-destructive testing, but unfortunately, NDT has very limited value in actually predicting the compressive strength. How do we actually get the compressive strength? We take a core through the structure, right? We take a core and establish whether the concrete in the structure has adequate strength or not. Okay, for strength, we understand all of that, and there are acceptance criteria also that are very clearly specified in IS 456. Now, what about permeability? If at 28 days, my permeability value does not match up, what do I do? Or my shrinkage is much higher than what is prescribed, or rather is given as a performance standard, what do I do? Can I do anything on the structure and measure it? Concrete in the structure is already shrunk. Right? No, pulse velocity is only giving us some indication of the soundness of the concrete in terms of whether the voids are properly closed because of proper compaction or not. UPV is not going to give you anything about shrinkage or permeability, right? You have to actually test these parameters. Unfortunately, by then it's already too late. You can't do anything. So the issue with performance specification is how to implement it. How do we ensure that what we set as a performance parameter gets implemented, and how do we take action when the required quality is not met? For strength, we understand it's not a big deal, right? If a column concrete shows of lower strength, both in the specimens and in the cores, we say that, okay, do a jacketing, increase the capacity of the column. Simple enough, right? What do we do for lack of required impermeability in the concrete? Then we have to start looking at what is an option for coatings, which will reduce permeability, right? How do we reduce the water penetration characteristic? All of those things need to come into play when we start thinking about how to implement durability specifications. So some examples of specifications in the early days, early 2000s was when the durability specs really started playing a role in construction projects. Many of these examples you see are from North America. Of course, now we have a lot more implementation in the Euro countries also, because the Euro codes for concrete have started taking cognizance of durability implementation. But these are very early examples from North America. You have here the New Brunswick draft specification for bridges, which specified an RCPT value and shrinkage value for the concrete. Here they said 1000 coulombs is the limit without corrosion inhibitors, and 1500 is the limit with corrosion inhibitors. Now, why is the limit increased when corrosion inhibitors are used? It increases what? Okay, now if you really look at the RCPT, your answer in one way is correct, that using corrosion inhibitors increases the threshold at which corrosion initiates. Fine. But the aspect that is contributing to this higher Coulomb charge is the fact that corrosion inhibitors come with ionic species that increase conductivity of the concrete. So when your conductivity increases, the charge pass through concrete will also automatically increase. But that doesn't mean concrete is of a poor quality. Okay. So here that aspect is being paid attention to. It's not, threshold is a big risk to take. Here the aspect that you need to address is the fact that you are increasing the ionic conductivity, which increases the charge passage through the concrete. Now in terms of shrinkage, it says 0.04% is the limit for superstructure, 0.05% for substructure, and this is again specified at a particular age, 7 days. Okay, so this was used as a performance parameter. In Calgary City high performance concrete specs, RCPT was used. Limit was less than 600 coulombs. And then they said that, okay, limit is 600, but if you give me concrete which is 600 to 1200, it's acceptable with a $40 per cubic meter penalty. Okay, that's another way of implementing and ensuring that the contractor is paying attention, right? If they don't meet the spec of 600, they pay a penalty. Now, of course, a specification cannot simply work with penalties. There should be bonuses also. Let's say you meet your specification 80% of the time, there should be a bonus, right? And reduce your failures to less than 10% or 15%. There should be a bonus clause also, right? These are some ways in which such things can be brought into specifications. In Port Authority of New York and New Jersey, RCPT was again used, and they said for pre-qualification, that means when the mix is actually tested in the lab, 1000 coulombs is the limit. But when you supply concrete to the site, you know that there's going to be a lot more variability. If you look at this test method carefully, it says that the variability can be as high as 20 to 40% in this test method. For strength determination, what is the typical variability that we expect for strength determination? When you determine compressive strength, what is the extent of variability that? No, that is the design of the concrete for a target strength based upon your characteristic strength. I'm talking about when you test 3 cubes, okay, you are allowed up to 15% difference, but typically when you test cubes, you'll see that your variability is restricted to 5 to 10%, not more than that, right? In strength, the variability is small, but in durability testing, variability can be sometimes as high as 50%. So you need to design your values very carefully. Okay? So here, that's why they say for production concrete, less than 1500 coulombs is okay, and that too in 80% of the test. That means in 20% it can actually still fail that, right? So they don't want to play on the quantitative nature of the result. They want to ensure that people understand that the variability in the concrete on site is going to be higher than the lab. So you're allowed that variability, but at the same time, you pay attention to the quality. So that's how they've implemented the durability specs. So what are the steps in durability design? First is identifying the right exposure environment and the associated durability issues. So in Chennai, we know that corrosion due to chlorides is the durability problem that we have to primarily work against, right? Understand how transport of liquids and gases will occur into the concrete. What is the mechanism of transfer of these liquids and gases in the concrete? Is it by diffusion? Like if you have a column standing in seawater, right? Here the concrete is completely saturated, right? Under the water level, concrete is completely saturated. So there is driving mechanisms of the liquid into the concrete which involve penetration due to pressure. As you go deeper and deeper, the pressure of water increases. So permeation can happen. And the chlorides in the seawater are higher than in the concrete, right? So diffusion of chlorides can happen. So all these happen in a saturated condition. But here, above the water surface, there is drying and wetting because of splashing and because of tides and so on. So there may be some absorption also happening. A dry material absorbs water, right? So absorption is happening in addition to all of these other physical and chemical effects. So you need to be aware of how are these liquids getting transported, and your test methods have to address those transport mechanisms. That's why I was saying the choice of simply using RCPT and WPT in all our projects, it's not a good idea because it's not really paying attention to this aspect. Okay? So understand how transport will happen in the concrete and select tests that reflect the correct transport mechanisms. You have to select the test that we have a range of tests available. to select ones that will reflect the correct transport mechanism. Now, of course, in the site, you won't have one transport mechanism that drives deterioration. There'll be a multiple combinations of transport mechanisms. You have to address all of those, okay? And set the limiting values of the test that need to be achieved. Like in the previous slide, I showed you 600 coulombs or 1000 coulombs. Those are limiting values. Perform design trials to obtain the right combination of workability, strength, and durability. This is during the pre-qualification process. And then in site, you need to look at acceptance criteria. How much variability are you allowing in the production process? So all of these are steps that you need to follow in durability design. So that is why it is quite a cumbersome approach to apply to real construction projects. It requires a lot of pre-planning. And if you don't do that pre-planning, things can go haywire. Okay? We are comfortable with strength-based design, no problem. People can handle it. But when you have to pre-plan, when the producer and the contractor and the owner, they need to agree on a strategy for controlling durability, all of that needs a lot of pre-planning, a lot of education, a lot of understanding on the parts of all the parties involved. So conventionally, of course, as I said, we are looking at laboratory cured specimens, but in a performance approach or specifying a performance approach, you can also start looking at field based specimens. I'll give you an example. I was called to inspect a concrete that had not set in 3 days. Okay, this concrete was poured into a column. After 1 day, the foreman saw that the top of the concrete had set, or it looked like it was dry enough, so they removed the formwork. All the concrete simply collapsed, right? So at the 3rd day, I went there, inspected, the concrete was still looking not set, but I could smell the admixture. They had added a lot of admixture, which probably caused a delay in setting. Then I went to the lab and I said, okay, you may have made cubes from the same batch, show me the cubes. They got the cubes. Cubes were in perfect condition. They tested the cubes. Cubes gave perfect strength. 3-day strength, which was expected, was given by the cubes. So what happened here? The site concrete had some tampering. What tampering? Addition of additional superplasticizer to ensure that they got workability at the time of placing the concrete. This concrete was getting placed late at night, probably very few people actually checking. And secondly, concrete may have been standing for too long and the site may not have been ready to receive it. As a result, the delay caused the workability to drop. They added more admixture to increase workability, overdosed, and as a result, concrete did not set. So one way that this could have been avoided is that the concrete cubes could have been cast at the time of placing concrete in the structure instead of in the QC lab. The concrete delivered in the QC lab in this case was completely different from what was actually going into the structure itself. So that is one way to look at controlling the sampling itself, can be leading to a better control on the durability, right? So you have to reflect the conditions of the actual structure. That's what the aim is. So as far as possible, if you can get to the quality of concrete in the structure, you can ensure durability. Okay. Now, the other aspect of this process of performance specs is the limitations on supplementary materials, supplementary cementing materials. Oops. The limitations of supplementary cementing materials can be overcome to a large extent. In many cases, we are bound by our codes saying that you can't use more than so much percentage of this, so much percentage of that, and so on, right? If you start following those prescriptions, we are very restricted in what we can achieve in the concrete. Like I was saying for that example, the tunnel segment, right, where 45 MPa strength had to be increased to even 80 to 90 MPa to achieve durability result. In that case, a simple substitution of the cement with a fly ash or a slag would have been enough to actually achieve that durability result, right? That could have actually led to the right durability result without worrying too much about the increase in the strength. And all of this is absolutely important because we want to lower the overall clinker factor and get improved sustainability impact. Because ultimately, it's not enough to just say that I've made my concrete stand for 50 years. It's important also to say that I can make my concrete stand for 50 years and yet produce a lower carbon dioxide emission as compared to concrete that stands for 20 years, right? And that can only be done if I have a good control on the material combinations that I can use for the concrete structure. So clinker factor is the amount of plain cement that is there in your concrete. So let's say I'm using 70% cement, 30% fly ash, the clinker factor is 0.7. So worldwide, and India, of course, because a lot of the concrete is being used for residential purposes, cement is also being sold primarily for the residential market. And in the residential market, only the Portland porcelain cement, fly ash based cement is actually available, because of which our clinker factor in India is already down to about 0.7 to 0.75. In China, it's down to about 0.6 because they use a lot more of slag cements and combinations of slag and fly ash and so on. So the aim towards sustainability is, of course, to get to that lower clinker factor, but not at the cost of longevity, not at the cost of durability of the concrete structure. So all of these have to happen together. The other advantage of performance specifications also include use of unconventional aggregates, right? Sometimes we can use recycled concrete aggregate or manufactured material from industrial waste, like slag, steel slag aggregate and so on, right? You can use treated wastewater. Right now, the prescription for water is that you use something which is potable, fit enough for drinking. Already people don't have water to drink. If you insist that they have to use drinking water for concrete, where will people go for drinking water? So it's important that we also look at reducing the usage of high quality water for construction. Of course, that doesn't mean we go and use chloride contaminated water. We all know what happens because of that, right? So here, performance specs allow a better allocation of roles and responsibilities between parties. Everybody is aware of what their deliverable is in the project. Rather than have this confusion about who's responsible, people always find to put their fingers on others to blame, right? Not realizing that when you're pointing one finger, 3 other fingers are pointing towards you, right? So when you have to point all 5 fingers. Yeah, so some examples of specs that can be followed for applications, like if you have pavement quality concrete, you can follow specs that define what is the flexural strength required for the concrete, the abrasion resistance, because these two are the primary criteria driving performance of concrete pavements. You can add freezing and thawing resistance if you are working in a climate which is cold, right, where like freezing thawing likely to have a damaging problem as far as concrete is concerned. For a bridge deck, the specs that you can think about are permeability, because bridge decks have to be impermeable. The concrete for the bridge deck should be impermeable. Shrinkage is a major issue there, because you need to ensure that cracking does not happen because of excessive shrinkage, and flexural strength, because it's most bridge decks have to perform in terms of their flexural strength requirements are concerned. Concrete column in seawater, I already described this issue of what is below the waterline, above the waterline to you. Compressive strength obviously is important because you have the damaging effect of the waves, right, which is affecting the concrete structure on the surface. And you can have a combination of different types of specifications like chloride diffusion coefficient, the water absorption, and the permeability. These can be additional specifications that you can give for the concrete columns in seawater. The most critical zone to define in concrete columns is the zone which is affected by the tide. That's the most critical zone. That's where you need to define your extreme condition for seawater. So all this is good, but why do we not want to use it everywhere? Why? What are the roadblocks? We already discussed this briefly, so I'm just going to be quick about this. What do we do when the durability requirement is not met? With strength, we have an idea. With durability, we really don't understand what to do. One example I'll give you. Recently, there was a case of a concrete structure which was being made where we were using, I think, 400,000 cubic meters of concrete totally. Massive amount of concrete was used, 400,000 cubic meters. And the durability test of water penetration resistance was actually specified. They had, I think, 6 to 7,000 sets of measurements. One set failed. They didn't know what to do. One set failed. All of the 7,999 sets passed. One set has failed. So what is the safeguard? What do? Do you break open the entire structure? 400,000 cubic meters of concrete. Probably not, right? So you need to figure out what is the way forward. Of course, those things have to be taken on a case by case basis. You can't write a code around that, right? Exceptions can always happen. There may have been a problem with the instrument on that day. Who knows, right? So all of those things need to be looked at beforehand. That's part of the durability planning process. Again, which test is the best to use? Many of them have combined transport mechanisms anyway. For instance, you have RCPT, which we call as a very important test measure. It actually is not reflecting very clearly the permeability of the concrete. It has another aspect of applied potential difference across the concrete, which drives a different kind of a transport mechanism called migration. Ionic species can migrate under the effect of an electric field and not just diffuse to the concrete. So what are we actually testing, right? What is the impact on the progress of the project and the cost of durability testing? It's important to address these issues. Otherwise, we'll really not be able to satisfy the requirement for so many different tests that we do in addition to the strength. So the way forward obviously is to plan for durability in the construction process itself. So what can we do? What are some steps in planning? Before starting, as I said, you have to look at what are the anticipated problems that you can expect in a given environment and choose the appropriate durability design methods or test methods. And as I said, in practice, no one test can give you a complete understanding of concrete durability. Use a combination of test methods, right? You have to look at resistance to ingress of liquids like water and so on, gases, carbon dioxide, and sometimes chemicals. Okay, so you need to have initial testing to be completed and establish any correlationships in the lab. That's very important because you can't keep on testing, right? If you have a sufficiently robust laboratory study, then you can get these correlationships established beforehand before you actually move into the actual production process. During construction, you need to look at what is your sampling frequency for which you do the durability tests, right? You have decided the test to do, but what is the sampling frequency? You have to be aware that all of these durability tests are not instantaneous. Each test takes hours and hours, right? The rapid chloride penetration test, it's not that rapid. The specimen conditioning takes 18 hours, test takes 6 hours. So you need 1 day to do one test. In strength, you hardly need 5 minutes to break 3 cubes, right? So you can't obviously have the same sampling frequency as you have for strength. If you do that, your construction project will not go on. You'll be testing all the time. You obviously don't want to do that, right? So a simple prescription here could be to use 3 samples for every 500 cubic meters of concrete during the initial stages where you don't have a hang on how the quality of concrete is during construction. As you start getting greater confidence, then you can increase the duration or reduce the frequency. Let's say take once in every 1000 cubic meters, depending upon the size of your project, right? Again, all of these have to be agreed between stakeholders at the commencement of the project. Otherwise, in between, if you say that I'm going to reduce my extent of durability testing, the client will come and say, okay, why suddenly you have lost your focus on quality? What the hell is happening here? All of this have to be perfectly agreed to in the beginning of the project. Then conformity assessment, of course, you need to have appropriate threshold values like those 600 coulombs or 1000 coulombs, right? And then acceptance criteria. What can you expect when you have variability in the durability test method, right? How do we allow for that variability in construction? And an important part of this entire durability approach has to be a good quality third-party testing, and the labs need to be accredited to ensure that the testing is producing results that are reliable, right? Very often people report very weird test numbers, right? You have to ensure that the equipment that are being used for the testing are properly calibrated and the results shown by the test are reliable. Then on constructed elements, you can have some limited amount of tests. For instance, the cover meter survey. The cover meter survey could be a very useful test method that can at least help you assess the cover or the deviation from the cover in the actual construction project, right? If you see that out of the chosen elements, 9 out of 10 are showing a cover which is less than 10 millimeters away from your intended target, that means the quality control has been okay. If it's been more than 10 millimeters away from the target, then you know there's a problem. People have not done their job properly. Okay. So all of that can be assessed. It's not going to be just relying on the kind of blocks that we use during the preparation process. Now, tolerances should be clearly specified in the specification. Is 10 meters acceptable? Or not 10 meters, 10 millimeters acceptable, or should it be 5 millimeters? That is something that needs to be brought into the specification. For everything, we can't say code says this, code says that. The specification is the main document in a construction project. It's not the code. The code is for assessing situations where we don't have prior experience. The code is helping us in those kinds of situations. The specification is the governing document to be followed in a construction project. That's where all of these things need to get reflected. Because code cannot be all inclusive. It can't keep on thinking about what can happen here, what can happen there, how do I include this, how do I include that. That's not possible in a code. A code has to be simple, easy to understand. If you look at the code carefully, in several segments it clearly says it's as per the discretion of the engineer on site. Code doesn't say that you have to restrict your fly ash content to 50%. Engineer can decide if he has data, right, that 70% fly ash is able to give you the required performance. Why not use it? It's reducing cost of your concrete. It's increasing quality, right? So in such cases, the engineer has to pay attention and be able to implement these strategies. But why is it not happening enough? No one wants to take the risk, right? The code is always there. I did everything according to codes. So the engineer passes on his risk to somebody else. Says, okay, I'm not taking risk. I'm just following code. Okay. So that's where the main issue is. Okay. That over reliance on the code is leading us to suboptimal designs. Okay. It also sometimes helps for us to have structures which don't fail in spite of the kind of construction quality that actually goes in. That's because we have over designed multiple number of times. But the specification has to address these issues, because ultimately we need to start thinking like engineers. We are not contractors, we are engineers, and we need to design structures based on optimal design considerations. We can't just think that, okay, something will keep going wrong because of which I'll keep increasing the factors of safety. That's not the way that we need to design. The other test method that is actually getting a lot more useful is this electrical resistivity measurement on the concrete. Because it's non-destructive, it can be done very quickly, and you can get an estimate fairly quickly on the actual construction site. Now, you know very well that concrete has porosity, and if moisture is in the pores, it will lead to conductivity. So that means if your pores are connected, your conductivity is going to be high. In other words, the resistivity is going to be low. You also know that when the pores are connected, the permeability is high or durability is low. So if you convert that to a positive parameter, take the inverse of conductivity, that is the resistivity. The higher the resistivity, the better the concrete quality in terms of durability. Okay, so you can measure electrical resistivity fairly quickly and establish that as a control strategy for your concrete structure. Okay, it's quite easy to perform in the field. There's handheld resistance meters available. In fact, we have a startup from our research park which is also making one such equipment. All of you who are going to be in practice, I urge you to make use of that equipment and look at the quality of the concrete through a durability perspective also. And you can also do this on your specimens that are removed from your curing for the testing for the compressive strength. Just before testing compressive strength, you can actually measure the resistivity also. Establish some of these parameters so that you get confidence in using these instruments on site. Of course, very important to remember is that this test is very susceptible to even small changes in the moisture content of the concrete. So you have to ensure that concrete is completely saturated at the time of testing. And on site, when you're actually doing actual constructed elements, you need to also account for the presence of reinforcement. If your cover is small, then the reinforcement also will affect the conductivity. Quite obvious, right? You are passing a current through. If your reinforcement is there, obviously your conductivity will go up or resistivity will lower because of that. So you need to be aware of those things and ensure that you're doing the test appropriately. You can do a reinforcement location test and then choose one location which has less reinforcement available, perhaps. to do the resistivity test on site. There are several other preparations that are necessary to ensure durability. One is obviously the shape should be capable of promoting proper drainage of water. It's funny that I should even write this because it's common sense, but unfortunately, in many of our situations, this is one aspect that we don't seem to follow, including in our building science block ground floor slab. The previous design was such that the water which came in because of rain stayed there. Rainwater harvesting is not intended to be done on floors. It should be done in wells. Unfortunately, it used to be done on our floors. Water was available all the time, and there was no way to drain out this water unless you start using manual labor. That's not what you want to do, right? You want to design appropriate slopes at your terraces wherever water is likely to connect, is to ensure that water drains out. And that's the first principle of durability, is to design your structure so that water does not stay on in the structure, it goes away. Quality plan has to be prepared by the concrete engineer on site, a producer, sometimes the contractor. Third party certification is essential for RMC production facility, because very often you are getting concrete delivered from ready-mix concrete. The BIS has a quality criterion for RMC, which needs to be, there's a very clear code also with IS 4926 that all of these RMCs have to get certified with, and you have to ensure that you are buying the concrete also from the certified concrete producer. As an engineer on site, you need to ensure all of these things. If your concrete quality is bad to begin with, what can you do on site which can help, right? Transportation, handling, and placing and compaction. These are aspects that need to be paid attention to. Again, this is happening mostly without any engineering supervision. This is where most of the problems happen. So that means we are disseminating to the last line of people who are handling our project. When you are working with a steel structure, the production of the steel members is done in a controlled condition in the factory. But when it's brought to site, there are still skilled personnel involved to look at how do we prepare the connections, the bolts, rivets, and the welds. There are skilled personnel on site, right? On the other hand, for concrete, who's there? Nobody is there on site. The foreman is there probably, but the foreman is not looking at all the concreting processes that are happening. It's all in the hands of the laborer who's working with the vibrator, who probably doesn't know why excess water is bad for the concrete. They need to get their job done, right? So that leads to a slightly different problem also about the construction scenario in India and other developing economies, where we have this issue of lack of appropriate work conditions for our workers and lower wages. I think these are issues that will drive durability a lot more than any technical aspect that we're discussing here. Unfortunately, that's the reality, and we need to ensure that we are finding ways to overcome that, right? Just an example, one of our lab attendants wanted a job in a construction company. So I got him a job with a company that was handling a major infrastructure project at that time. That guy was posted on the site and asked to make concrete cubes for testing for a continuous period of 48 hours. He was continuously making cubes for 48 hours. They didn't give him a break. That guy landed up in a hospital after that, and he said, I don't want to go back to this job. These are the harsh realities, the conditions that our workers face on site. Imagine if this kind of a person is going to be making your cubes for 48 hours at a stretch. Where is the quality on the concrete that you'll get? Or your test results will give all kinds of weird values. Your non-conformance reports will be all over the place, right? I mean, these are realities that somehow I'm really upset that our construction companies are not addressing in a good way. Anyway, then finally, the curing of the concrete. Adequate curing obviously is a must. You need to ensure that the curing strategy is designed properly and implemented with proper supervision on the site, right? Because there's only so much we can design. Ultimately, the control of how the application process on the site is in the hands of people who are not very qualified. They are simply there doing the work, but they need to be brought in to understand the importance of that work. That's the last line of defense, right? Yeah. Oh, okay. Yeah. So I wanted to bring that point. Yes, I wanted to bring that point of course, towards the end, when I discussed this variability in the durability test methods, there was an extensive study done in South Africa. Professor Mark Alexander, who is one of the top proponents of performance specifications, he had conducted the study of road projects executed by the South African National Roads Agency, where they looked at the concrete quality supplied for the projects from various RMCs, and also the concrete quality assessment in a precast factory which was supplying girders for the same construction project. They found that the variability in the precast factory was at least 15 to 20% lesser as compared to the concrete that is supplied on site. So definitely in precast operations, even the variability in durability tests can be brought down significantly, because you have a controlled environment, you have generally a lot more qualified personnel handling precast operations as compared to on-site construction. So ensuring durability in precast construction, or at least in the precast panels, is much easier as compared to doing this in a on-site construction. However, if you don't pay attention to the connections on site, then you are creating more problems, right? Because ultimately, correct, absolutely. Because precast, the entire performance is in the connections. If you establish those connections, the site properly, in steel, again, as I said, it's bolting, riveting, and welding. In concrete, you have to actually do in situ construction or in situ concreting to establish those connections. So those have to be of the right quality, and that's where perhaps some link to your durability assessment and the design strategy has to actually come in. I'll give you some examples of durability specs in construction projects, just to show how they've been applied. Not just durability specs, but design for durability in construction projects. Some of these are very well-known projects, like the Øresund link between Denmark and Sweden, the Confederation Bridge in Canada, New Panama Canal, and metros, which are being constructed everywhere. Many of these are from projects undertaken by L&T, so I thank them for giving me this data, like the metros as well as Statue of Unity. So the Øresund link is a very unique bridge tunnel system that connects Copenhagen to Malmo. So here you have three components. You have tunnel as well as dredged island and bridge. The concrete structure was designed for a 100-year design life. Okay, and it was achieved with cementitious contents, not cement, cementitious. That means including all your supplementary materials of 345 to 450 kilogram per cubic meter. Okay, now I'll give you another example later where the cement content minimum prescribed was 450. Okay, now that I'll come back to later, that produced other problems. But here the water binder ratio ranged between 0.32 and 0.42, and they were able to actually control the design life based on that. They used a particle packing methodology to ensure that they can minimize the voids in the concrete, okay, by appropriate design of the sizes of the materials that they're using. They used a ternary blended cementitious system with fly ash and silica fume, right? And with this, they were able to achieve this 100-year design life. They did the modeling based upon the European approaches, the Duracrete approach, to ensure that they are able to satisfy this 100-year design life against chloride attack. The Confederation Bridge in Canada is a 12.9 kilometer long multi-span box girder structure. So here they had a seawater attack consideration, of course, chemical attack because of chlorides and sulfates, and then freeze thaw and abrasion. They again designed for a 100-year design life. To ensure that they are not having any problem of alkali aggregate reaction, they chose a low alkali cement. And then they also used fly ash and silica fume to reduce permeability. Water binder ratio was controlled between 0.25 and 0.36. Air entrainment was used for freezing and thawing resistance. And they had a durability value that they had to match during the project, and that was 3.5 into 10 power minus 13 square meter per second. Now, this is very difficult to actually achieve. 10 power minus 13 is a very stringent durability criterion. To give you another example, the Mumbai Trans Harbour Tunnel, the concrete was actually having a durability specification of 2 into 10 power minus 12 square meter per second. Okay, so the concrete was tested as per one of the durability test methods there. The Panama Canal is where the electrical resistivity was actually applied as a means of, actually there's a small mistake here, this is kilo ohm. I'm a little confused about that. There's some mistake there in that value. So what they did was they had a durability specification of an RCPT, rapid chloride penetration test limit of 1000 coulombs, and they had a restriction on the maximum temperature of the concrete placement because these were massive members. Okay, the on-site resistivity testing was used for quality monitoring of the concrete. Okay, and they established through laboratory studies that the benchmark electrical resistivity to be obtained in the concrete was so much for an RCPT value of 1000 coulombs or better. And using that, they ensured that the concrete that was in the structure was of the right quality that they needed based on the test from the laboratory. So this is a project executed by L&T, Riyadh Metro. So here, this is a structure that is 400 kilometers away from the sea, so you don't have any seawater attack or chloride attack. Carbonation was the considered mechanism in this case. Carbonation depth after 100-year exposure was established to be 35 millimeters. That means they did modeling to ensure that they understand how deep the CO2 will penetrate into the concrete, that was 35 millimeters. And they had a cover that was more than that. So that's how they controlled durability in the structure. Okay, and they also had several tests that were specified for assessment of durability in the concrete. And they also did a carbonation depth measurement on the concrete directly also. In the Doha Metro, they had established that there was a risk of chemical attack in addition to carbonation. So they had to design the substructure, that is a foundation, against chemical attack. So this is in situ concrete in contact with the ground. And look here that they have described the concrete mix to be a mixture of cement and slag and silica fume. They go for a cement content minimum, cementitious content minimum of 380. Additionally, they have what is called an additional protective measure, APM, of a fully bonded waterproofing membrane. So to avoid chemical attack, not only did they look at the quality of concrete, look at here, they have the quality of concrete based on sulfate attack resistance, RCPT, chloride migration, water absorption, all of these were to be met in the concrete. Apart from that, they also gave an additional protective measure. So depending upon the severity of the attack, you can choose to add an additional protective measure also. In Chennai Metro, we had a 120-year design life strategy again. 35 to 60 MPa grade concretes were used, and these were the durability criteria that were used, WPT and RCPT. Water penetration test of less than 10 millimeter water penetration into the concrete under a 5-bar pressure applied for 3 days. That's how the test is. And then you have RCPT of less than 600 coulombs. That was actually applied. And they had crack width criteria also for the different elements of your underground construction. They again had a fire resistance performance also, and they defined the cover based upon the fire resistance performance. So all of these are depending upon the kind of exposure, the kind of expected issues that you have during the overall performance period. You can then define these criteria and then ensure that you are able to meet these demands from the concrete mixture. Now, Statue of Unity, here it's a 100-year design life concrete that was designed. Various grades of concrete, M50 to M65 were actually designed, and the cover was different based upon whether it was a superstructure or the foundation. For the foundations, the provided cover was 75 millimeters, and they actually did a design life calculation where the cover was only 40 millimeters required to ensure that in 100 years you don't have any risk of issue with carbonation. Now, here the shear walls were massive, so they did temperature control on the concrete, right? And now, unfortunately, this was the project in which the CPWD specifications were applied by the state agency, Gujarat state agency controlling this project. And they said that as per CPWD specification, when you're using M65 concrete, your minimum cement content should be 450 kilogram per cubic meter. Cement, not cementitious, cement content. Now, imagine having 450 kilogram cement in your concrete, which is massive, and still ensuring that you're avoiding cracking due to thermal effects. And that was a huge problem in this construction project, that the cracking, to avoid cracking, they had to look at possibilities of using extenders and ensuring that they make the strength criteria, but at the same time also ensure that the cracking can be avoided properly because of thermal effects. Okay, so these kinds of things need to be paid attention to. Now here the contractor also did not pay attention to the fact that the CPWD spec said that 450 should be used. That means there was no planning of durability, agreement on how control of durability should be done between the parties involved. Okay, so they had some issues because of that. They had some issues in terms of agreeing on whether payment is to be made for the project, or they had some issues which had to be resolved. Hopefully they're resolved now. Now, we also are moving to a new IS 456 in India. It has been in the works for a long time, but I'm hoping that it will come out within this year. There are attempts now to bring in durability provisions on the lines of what is currently available in the Euro codes as well as in the FIB model code. So here a concept of service life and durability design has been introduced, and provisions for durability design for a 50 to 120 year period have been given. There's a deterioration mechanism based exposure classification, which was not there in the previous IS 456. There we were only working with general exposure environments. And a climate map is also being created linked to durability problems. QC levels for durability preparation have been looked at for the first time. And limit state design is there for carbonation and chloride ingress. I'll just give you some snapshots of what is being done there without getting too much into details. And they've also looked at additional protective measures to tackle difficult situations and circumstances. So in carbonation induced corrosion, they are looking at prescriptive design for less than 50 years design life. Right? They're looking at minimum cover to rebar, limiting values for your water binder ratio, cement content, minimum cover, nominal cover, and a durability test requirement in terms of electrical resistivity. This is for 50 years or less. But when you are beyond 50 years, the IS 456 will say that you need to do a durability design. A limit state probabilistic durability design method will be done, which will involve the design parameters like the carbonation or carbon dioxide level and weather coefficients. For instance, even if we have high carbon dioxide levels, our humidity carbonation does not become a dominant mechanism in. Whereas if you go to Bangalore or Hyderabad, which is far away from the lower level, those are ideal conditions for carbonation related. Then resistance is defined in terms of carbon. A concrete which has a lower carbonation rate, a concrete that cover that is higher will have a greater carbonation. And verification is called the carbonation coefficient from durability tests done in the lab. Concrete structure which has a design life of more than 50 years, we need to start now following the steps of durability design. Okay, so this is needed or mandated in the new IS 456, and again a partial safety factor definition is also given for carbonation coefficient values, cover values, and so on. And the initiation period is defined based on this equation, which is essentially just a typical variation that we see in terms of the weather, in terms of carbon dioxide concentration, and so on. And there is also a propagation period given. So you know that in corrosion process, there's initiation, that means the point at which steel starts corroding, and how fast it corrodes, that's a propagation process. So both these have to be addressed. So here a propagation period is also considered. In many models, the model stops at initiation itself. No risk is taken beyond that. But here, a suggestion is that we consider a propagation period also. Similarly, for chloride-induced corrosion, prescriptive design for less than 50 years and durability design for more than 50-year design life with appropriately chosen design parameters and verification of the chloride resistance parameters from actual testing. So this has been given as an example. Again, partial safety factors are there for your design values, for your surface chloride content and your chloride diffusion coefficient. And then we choose the fixed law solution, error function solution to fix second law of diffusion to establish the change in chloride concentration with respect to the depth into the concrete structure. There are durability provisions provided for other exposure classifications also, like sulfate attack, for instance. There are modified tables now with better definition of exposure environment, which were not previously available. There's a table for air content for freezing and thawing. And then for alkali aggregate reaction, there are prescriptions of accelerated mortar bar tests, which were not really indicated in the previous version of the code. And there's also, as I said, suggestions for additional protective measures, which are important when you are actually dealing with unprecedented situations. You can't always rely on high quality design of the concrete. You have to look at additional measures in some cases, depending upon the importance of the structure that you're designing. Right. So to summarize, of course, the performance approach gives a rational means of concrete design. Without relying just on prescriptions, we go a little bit beyond, understand the mechanisms that can actually affect concrete deterioration and actually design the structure for that. We can provide a quantitative meaning now to service life. Earlier, qualitatively, we are saying, okay, yeah, this will last for 50 years, but now we can quantitatively say, if you design it with this strategy, the structure will last for 50 years, right? In important aspect of performance specification is that you are encouraged to do innovation in material selection. You don't have to be rigid about the boundaries that you set for certain types of materials. But as I said again before, there are challenges to successful implementation, because unless we design our process to be a collaborative one, we'll never be able to actually apply this approach in practice. Collaborative means everybody has to be on the same page. Now there lies the biggest conundrum for Indian construction. The contractor is always assumed to be doing something wrong. That is a rule of law as far as construction projects in India are concerned. The owner thinks that the contractor is out to cheat them, right? Sometimes, unfortunately, the contractor also does not put in place safeguards that clearly show that they are actually applying themselves well enough. So this is a problem that needs to be tackled. If really we are to apply durability specs, everybody has to come on board together. As I said, it's a participative process. It cannot be done by any single person. The owner, the PMC, the contractor, the concrete producer, if it's different from contractor, all of them have to actually come together to make this possible. Many of these thoughts are given in our handbook on concrete durability, which is available from Indian Concrete Institute. A newer version will also come in, which addresses issues of cracking also. This newer version is expected to come to, later in the year. This version was released in 2019, so it's already about 6 years old. So we have made some changes to ensure that latest literature is also reflected properly in this handbook. It's a very valuable resource to have for all practicing engineers. I'll urge you to get this from ICI. Yeah. Yeah, so that's what current approach has been, to ensure that these things that I was talking about have also been brought in to some extent, and understanding has been brought into the durability handbook from ICI. Right, thank you all very much. Again, much of the work that I've talked about and is from the Center of Excellence and Technologies for Low Carbon and Lean Construction, which involves 15 faculty members from our building technology, construction materials and management area. Thank you.